Okay guys, so in the last two videos we were talking about radioactive decay, and we were filling in these tables using our reference table. And in this course we're looking at 4 different radioactive elements: potassium-40, rubidium-87, uranium-238, carbon-14, and here are the half-lives. Half-lives are fixed, they do not change. And just to review from the other video, the half-life represents the amount of time that it takes for half of the radioactive material to break down into a decay product or non-radioactive form. So, for example, if we go back to carbon-14, if we had a pound of carbon-14, it would take 5,700 years, or 5.7 times 10 to the power 3 years, for half of that carbon-14 to become non-radioactive nitrogen. Now we can use this idea of half-lives to figure out the age of an object, and that's where we're headed. So let's move forward. Out of the half-lives that we looked at and the elements that we looked at, carbon-14 has the shortest half-life, only 5,700 years, which again might sound like a long time, but compared to the other half-lives, exponentially smaller. And because of this, carbon-14 is useful for finding the ages of more recent living things. Because it has a relatively short half-life, it's very useful for studying ancient artifacts. If you wanted to try to figure out the age of an ancient Egyptian mummy, carbon-14 would be great for something like that. It would be good for looking at things like wood, old wood, like maybe somebody discovers a shipwreck and wants to figure out, what century the ship was from. Bones, we can analyze skeletons. We could look at things like leather and other ancient artifacts. But if we want to go back further in time and figure out how old, say, a dinosaur bone was, or how old maybe the oldest rock on the Earth is, well, carbon-14 is just not well suited to that. We need a substance with a much greater half-life in order to do that. And in that case, if you want to figure out the absolute age of something really old, you might look to uranium-238 or maybe rubidium-87. Carbon-14 is just best suited for things that were more in the recent past. Ancient artifacts, Native American artifacts, things from ancient Rome, ancient Greece, ancient Egypt, and so on. But if you want to really find out about old things, really old things, we need to look at those higher half-lives. So let's take a look at an example problem. In this example, we'll say that white in our legend represents the radioactive element. Let's say it's uranium or something like that. In fact, let's use uranium. So we'll say we have uranium 238. And uranium, as we talked about in one of the other videos, breaks down into the decay product lead. Lead is not radioactive. So uranium is radioactive. Again, it gives off particles from its nucleus. Lead does not. Lead is stable and is considered to be the decay product. It's a stable element. It does not give off protons from its nuclei. So it's a stable substance. Uranium is an unstable material. So let's say we have a piece of uranium. And I think that sometimes it's nice to work in percentages or fractions even. But if it's, say, 100% uranium, it's pure uranium, it's 100% radioactive, well, it's completely unstable. But after a time period of 1 half-life, which for uranium would be 4.5 times 10 to a power of 9 years, so quite a bit of time. After 1 half-life goes by, half of that uranium is going to be converted into radioactive or stable decay product. So what we end up with is a situation where after one half-life, half the material is radioactive, and half of it is that stable decay product, lead. So after we go through one half-life, we have our uranium. We have one half of the uranium. This is, again, that process of transmutation. We have half of the uranium remaining as uranium, and half of the uranium, original uranium, transmutating into lead. And we have half of the original material. We have a 1-to-1 ratio, where we have equal parts uranium and equal parts lead. And again, uranium is the parent product, and lead, the non-radioactive stable material, is what's called the decay product. Now let's say another 4.5 times 10 to the power of 9 years go by. We've gone through 2 half-lives now. So now we have our decayed material from over here. Now if we take this uranium and we split it in half, because another half-life went by, well, now we have even more decay product, and we have more lead. In fact, we have 3/4 lead out of our original amount, and now we're down to 1/4 uranium. We're now at a ratio of 1 part to 3 parts. 1 part radioactive uranium, 3 parts non-radioactive stable lead. If another 4.5 times 10 to the power 9 years go by, or another 1 half-life for uranium go by, well, now we have all of the radioactive or stable decay product from before. Now we're taking our 1/4 uranium and we're splitting that in half. And half of that is radioactive, half of it is decay, and we end up with that situation. And now if we divide this up into eighths, 1/8 would be uranium, 1/8 would be radioactive, and 7/8 would be decay or stable, and we end up with a ratio of 1 to 7. And of course, if we were to go through another half-life, another 4.5 times 10 to the power of 9, we could take this radioactive uranium and we could divide it in half again, and all of this would be decay. This would be uranium, or parent product. Which means now we have 1/16 the original, and now we have 15/16 decay or parent product. Okay, so this is showing how we go from 100% radioactive material, and then after each half-life, the amount of radioactive material gets cut in half and cut in half and cut in half. You'll never reach a point where your radioactivity goes away completely, but it'll become incredibly tiny. Now we can figure out how old something is by analyzing it in special equipment and figuring out the ratio. So if we analyze some ancient fossil or rock and we discover that there's this 1 to 7 ratio of uranium to lead within the sample, then we can figure out how many half-lives the sample has been through, and we can get a pretty good idea of its age. Most rocks have trace amounts of radioactive material in them. Barely enough to even measure, certainly nothing dangerous. But we don't have to be talking about nuclear power plants and atomic bombs to be talking about this process. There's natural radioactivity in most rocks, or many rocks. So we can look at the rocks and fossils that we find, and with the right equipment we can detect these trace amounts of radioactivity. Again, they're not dangerous amounts of radioactivity, very, very trace amounts, small amounts of radioactivity, but they can be analyzed, and we can figure out the ratio of radioactive element to parent or decay product, and we can figure out, and we can work backwards, well, how many half-lives has this sample been through since it formed? and then we could get a pretty good idea of the age of the sample. And again, carbon-14 works best for more recently decayed material. Okay, so that's just an overview of how this radioactive decay process would work, and how we could use it to figure out how old something is in geology. Okay, so we'll stop